This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are discussing critical radius of insulation in heat and mass transfer subject. So, here the mode of heat transfer which is taking place from one region to another region of the same object, or from one point to another point in the same object, generally used to conduction process now. The conduction process generally takes place in a solids. The main reason of transferring heat energy is the temperature difference between the two regions or the two bodies which are in contact with each other. So the rate of equations, the rate of energy that flows from one point to another point, it is governed by the Fourier's laws of conduction, which is according to the Fourier's law, the amount of heat energy that flows it is proportional to the temperature difference and the area of cross section, and inversely proportional to the thickness of the slab or thickness of the object. Or in other words, the quantity of heat energy that is flowing is proportional to the area of the cross section, thermal conductivity of the materials, and the temperature gradient. The temperature gradient is defined as it is the ratio of change in temperature per the unit length of the object. So these equations can be written as now Q is equal to minus of K into A into dt by dx, where K is representing the thermal conductivity of the material. It is a property of the materials only, and A the area of the cross section, and dt by dx is called the temperature gradient, that is change in temperature per unit length. Similarly, for the heat transfer which is taking place in gases as the liquids by using convection process, the Newton's law of cooling generally used to determine the magnitude of heat transfer that is taking place. It is given by the equations Q is equal to H into AS into TS minus TF, where Q is the magnitude of the quantity of heat energy that is flowing, H is the coefficient of convection process, AS is the area of surface area, TS is the representing that is the temperature of the hot solid, TF is representing the temperature of the fluid. That means according to the equations, the heat energy is flowing from hot temperature of the body to the lower temperature of the fluid. Third is the radiation process. The heat is exchanged between these two bodies or the medium which are separated and not are in contact with each other is called radiation heat transfer. The maximum energy that is emitted as a radiation by a body at a particular temperature is governed by the Stefan-Boltzmann law, which is expressed as EB, that is the maximum energy that is emitted, equal to sigma into A into T to the power of 4 now, where sigma is representing the Stefan-Boltzmann constants. Its values is 5.67 into 10 to the power of minus 8 watts per meter square per degree Kelvin. A the area of the cross section that is exposed to receive the energy. T is representing the temperature measured in degree of Kelvin. This generally the heat energy that transfers from one object to another object by using these three modes. That is, one is the conductions, the second one is convection, and third one is radiation process. Sometimes in liquids, the conduction as well as the convection process that is taking place to transfer the energy. Here thermal insulations. Here the thermal insulation is the medium generally which is not allow to flow of energy from one point to another point. another region. Generally, it is kept now. So, in many situations, in order to conserve the energy, in order to minimize the loss of energy through conduction convection process, the equipment which is used is called insulated. The thermal insulation material should have low thermal conductivity. This is achieved by solids by trapping air or gas in small cavities inside the materials. It also be achieved by loose filling of solid particles. Here an example I am taking now. Here it is one region of the solid. It is exposed at a temperature of T1, higher temperature. Here emission temperature is given, that is atmospheric air, assume it is air. Now this T1 is nothing but assume this is represented to 100 degrees centigrade. Hence, because of temperature difference, the heat energy flows from the region which is exposed to T1, that is 100 degrees centigrade, to Tn. So while moving now, the temperature of the object is gradually decreases from T1 to Tn. So the magnitude of energy that flowing is given by K into A into T1 minus Ta divided by, that is the thickness of the wall now. This is known as thickness of the wall now. But if the solid is there now, if it is having certain cavities or the impurities present inside it now, or the particles which are in loose, that white spaces are there, the rate of flowing of heat energy from T1 to Ta is decreased now. Or in other words, just we are preventing the flow of heat energy from the hot region to cold regions just by keeping certain loose cavities now, or by trapping certain air or gas cavities inside it now. So in particular in solids, the insulation, that is preventing of heat energy, that can be prevented by using inserting like fibers, mineral woods, cellulose and granular particles. Critical radius of insulation. Here just we are taking the example of a cylinder having certain length is there like this now. It is a hollow cylinder having internal radius is equal to R1 and external radius is equal to here R2 after insulations. Assume the thickness of the wall of the cylinder is negligible when comparing with the internal radius of the cylinder. The outer surface of the cylinder, assume it is covered with the insulation materials. That means because of insulation materials, the magnitude of energy that is flowing from inner surface to outer surfaces decreases. But this is only applicable for the conduction process. Because according to the conduction process, Q is equal to, we can take it as K into A into T1 minus T2 now. Because of insulation, the thermal conductivity of the material is decreases. Hence, the magnitude of heat energy that is flowing from inner surface to outer surface, that is decreases. Assume this value is equal to Q1 now. But since the object is exposed now, having contact with the fluid to the again metal surface, the heat conduction, that is heat flow, is also done by using convection process now. The convection process can be expressed by using equation Q is equal to H into A into T1 minus T2, where T1 is representing higher temperature and T2 is representing the lower temperature, and H is representing the here coefficient of convection process. But A is representing the that area of the surface area which is having in contact with the fluid. Because of bounding just insulations around the surface now, here the radius that is increases to R2, assume external radius. Internal radius is R1, because the thickness of the wall that is negligible when comparing with R1, and so because of insulation, the surface area that is increasing now. That means according to this equation, so Q is equal to H into A into T1 minus T2. T1 minus T2 is a constant now, the difference of temperature. H is also constant for the particular air material, but A is changing, the value is increasing because of insulation materials present over the outer surface of the object. So we can write it just Q2 is nothing but representing the amount of heat energy that is flowing by using convection process, which is equal to H into A into T1 minus T2 now. In first case, condension process, because of insulation, the thermal conductivity is decreased, hence the amount of heat energy that is flowing by using conduction process decreases. But at the same time, due to the convection process involved, the amount of heat energy is increasing now. Hence, because of net effect of convection and conduction process, because of presence of insulation materials over it now, the magnitude of heat transfer that is taking place, it is increases now up to certain limit now. That is the heat energy, the magnitude of energy that is flowing through the pipe when it is insulated at outer surface, it increases up to certain radius. After that, it decreases now. That is the radius at which the maximum amount of heat flows from the cylinder, or it may be the sphere, is called critical radius. So critical radius is the radius at which the maximum amount of energy that flows. So the resistance actually decreases just when the body is insulated, but because of Q2, the net energy that flows increases now. In case of cylinders and spheres, it is called critical radius, but in other objects, it is called critical thickness. The thickness of insulation corresponding to the maximum heat transfer rate from the pipe or cylinder is called critical thickness of insulations. The main application of the critical thickness is used in particularly electrical transmission cables. Because of increasing the surface area, the maximum amount of energy that can be dissipated from the cable so that it can maintain at a lower temperature. An expression for the same can be obtained by finding the rate of change of total resistance with the change in radius and equating to the zero, that is the zero slope conditions. Here consider cylinder of negligible thickness and length is equal to L now. This is the length of the, if the pipe is given, L is equal to length, and internal radius is equal to R1, carrying air fluid at a temperature of T1 and which is higher than the ambient temperature, that is represented here now T2, which is known as assume Tn. The cylinder is insulated by insulating materials having thickness T now. So because of presence of insulation materials over the cylindrical surface, the thermal conductivity K is increases, but it is also having effect on convection process. Because of increasing its surface area, the magnitude of heat energy that is flowing by convection process increases. Here the thickness of the insulation material is the difference of outer as well as the inner radius of the cylinder. Here the thickness of the cylinder is negligible, but R2 is representing the, here now, the insulated material when it is kept just over the cylindrical surfaces. Hence the thickness of the insulation is equal to R2 minus R1. Where R2 is representing the outer radius of the arrangement consisting of thin cylinder and a layer of insulating materials, and depends upon the value of thickness of insulating materials as shown in figure. So the heat transfer rate per unit length of the cylinder is given by the sum of the magnitude of heat energy that is flowing by using conduction process as well as the convection process. So combinedly it can be written as Q is equal to T1 minus T alpha divided by 1 by 2 pi R1 L HI plus 1 by 2 pi K L log A R2 by R1 plus 1 by 2 pi R2 L 1 by H naught. So H and H naught is representing the heat transfer coefficients of convection process, which are used in equation number 2 now. The heat transfer rate per unit length can be determined for different values of R2 now. So the maximum amount of R2 that can be obtained just by differentiating, that is resistance with respect to the radius and equating it to 0 now. The total thermal resistance of an arrangement is the sum of inside convective material resistance and conductive resistance of the insulating materials and outside convective thermal resistance now. Here we are taking R is nothing but representing the total resistance offered by the cylinder when it is having with the insulation to prevent the heat energy flowing from inside to outside now. The total resistance consisting here now. First one is the inside, here the fluid is there now. The fluid nothing but which is exposed to higher temperature, that heat energy has to flow from liquid to solid by using convection process. That is here now internal convectional thermal resistance. The second one is from inside R1 to this outside. This process is called here now conductive process. Again from outside to ambient air it is there, again outside convective process. So three are having the thermal resistance now. The total resistance is equal to thermal resistance offered just inside the cylinder. Second one is conduction. Third one is the outside convective process now. The total thermal resistance of the arrangement depends upon the value of R2, which in turn depends upon the thickness of the insulating materials. As the thickness of the insulating materials R2 also increases, resulting in increase of conductive thermal resistance and decrease in other convective resistance because of increasing, that is, surface area. Therefore, increasing in thickness of the insulating will either result in increase or decreasing in heat transfer rate depending on overall change in thermal resistance. Because here we are using the word now, because of presence of insulating material, it prevents the flow of energy by using conduction process, but at the same time the magnitude of heat energy flow from the cylinder from inside to outside that increases due to the convection process. Hence, the net magnitude of heat energy that is flowing, it depends upon the thickness of the insulating materials kept just over the cylinder. For heat transfer rate per unit length to be maximum, the thermal resistance should be minimum is required. The value of R2 for which heat transfer rate per unit length will be maximum can be obtained by differentiating the total resistance offered by the body, that is the sum of the convective resistance inside, thermal resistance, and outside convective resistance. This is called total resistance. Assume just if it is represented by R now, it is differentiated, that is rate with respect to the thickness of the insulating materials and equating to the 0 now. This nothing but gives its maximum amount of heat energy that flows at the given radius. So the equations here what we have taken earlier to now, this equation is now differentiating with respect to the R2, that is insulating materials, and equating 0 now. So we will get T by dR2, which is equal to, this is called total resistance now, 1 by 2 pi R1 into H1, 1 by 2 pi K log A, R2 by R1 plus 1 by 2 pi R2 H0 is equal to 0 now. So the first equation is there now. Since we are differentiating with respect to the R2 values, hence that first quantity it is treated as a constant. Hence the differentiation with respect to the R2 is equal to 0 now. The remaining are there now, 1 by 2 pi K log A, R2, a minus of 1 by 2 pi K log A, R1. That R1 is again constant now. The remaining values is equal to 1 by 2 pi k log a R2 in differentiation is 1 by R2 now. So you have taken minus of, here we have taken 1 by this integration of these values. Here R2 is there in denominator, that is 1 by R2. Here differentiation is equal to R2 to the power of minus 1. Here minus 1 divided by minus 1 minus 1. It is equal to R2 square. Here plus sign is there, that converted to negative. 1 by 2 values is there now. So it can be written as now 1 by 2 pi h naught into R2 square equal to 0 now. Since here 1 by 2 pi R2 is the constant values there now. Constant values. So after taking out now 1 by k minus of 1 by R2 h naught is equal to 0 now. In order to come, just this equation becomes 0. The first equation, first here factor is there, 1 by 2 pi into R2 which is equal to 0, or 1 by k minus 1 by R2 h naught is equal to 0 now. Since the first one is not equal to 0, hence second should be equal to 0. From this relationship we got if the first one is equal to 0, 2 pi, it is there, R2 is equal to 0. From this relationship we got R2 is equal to 0. That means nothing but there is no insulation. In second case now, if 1 by k minus 1 by R2 h naught is equal to 0, from this relationship R2 is equal to k by h naught, this is called here, at which it is having maximum flow of heat energy through the pipe. Hence this radius is called critical radius. These equations give the value of thickness of insulation for which heat transfer rate per unit length is maximum, as corresponding total thermal resistance is the minimum. The value of thickness of insulation at which the total thermal resistance is minimum is called critical thickness of the insulation. In the case of air surfaces, and in the case of cylindrical objects, it is treated as a critical radius. It is generally represented as air or C now. It depends upon thermal conductivity and convective heat transfer coefficient of insulating materials. The addition of insulating materials to bare surface will either increase or decrease the heat transfer rate per unit length depending upon the value of critical radius and radius of the bare surface, that is the A value. Okay, these are the textbook followed for collecting these materials. Unisya Singal, heat transfer a practical approach. The second one is R.C. Sachdeva. And reference textbooks we have taken C.P. Kodandaram and Holaman. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.